All right. Hey, Richmond. I think regarding that prompt injection problem, if you just filter out ZZ, that should prevent all your problems. Hey, good morning. Josh and I are real happy to kick off the tech track today at RVAsec. We are going to talk about how we have been harmonizing with large language models to find vulnerabilities. We work at Bishop Fox, and Bishop Fox does a lot of things. We've, in the LLM space, we've been doing both the security testing of large language models. We've got a coworker named Rob Reagan who will be talking about that in a webinar in a couple weeks. You should check that out. But we've been working with using large language models to find vulnerabilities. And we're going to break that down first with a demo. And then we're going to go into some of the prior work that others have done using large language models in offensive security. Josh will give a primer on end-day vulnerability analysis, which is where we've spent a lot of our time over the past couple of years. We are going to then deep dive into the approach that we have taken, combining those two concepts, large language models and end-day analysis. And then we'll try to leave some time for Q&A as well. Before we jump into the details, a quick intro about us. I'm Caleb Gross. I lead a team at Bishop Fox called the Capability Development Group.
And I'm Josh. I'm in that team, and I have a group of reverse engineers with me focused on vulnerability research.
Yeah, so the term capability development is a term that we borrowed from our former life in government. So if you're not familiar with it, a capability developer will work alongside of an operator or an analyst. So if they have a problem, if they need to break in, but they don't have an exploit, they'll go to a capability developer and say, hey, can you do a deep dive on this tech stack and give me a tool, give me an exploit. So that's a function we serve at Bishop Fox. We help the operators, consultants, analysts, developing new tools, techniques. I was an Air Force officer in a prior life, and Josh, as he mentioned, worked at DoD as well. We are taking a quick look here at a sample of some of the stuff that our team has released publicly over the past couple of years, and you'll see a trend of a lot of SSL VPN appliance analysis, and our focus just kind of follows what our customers tend to have on their attack surface. We've specifically spent a lot of time working in the Cosmos continuous security arm of Bishop Fox, where 24/7, 365, if our customer has a device and the vuln drops on that device, we will try to, as fast as possible, reverse engineer the vulnerability, work out an exploit, and help them test and make sure, see if they're actually vulnerable or not. And that has taken a lot of manual analysis, but we have been asking, could we use large language models to help out with some of the most more intense parts of analyzing potentially vulnerable code? And this gets us to the core question at the heart of this talk. Are large language models a revolutionary leap forward for offensive security researchers, or does it just amount to spicy autocomplete? It's up to you to decide. We're going to provide some evidence to suggest that the answer is probably somewhere in the middle, but we're not the only ones asking this question. I've just dropped a thread from Twitter from a few months ago that was part of inspiring us to even submit for this talk. Anthropic released Claude 3 and accompanied it with a sentiment that fully automated vulnerability research is changing the cybersecurity landscape. And it was swiftly met with some criticism saying, hey, this vulnerability was just hallucinated. This is not really the vuln, and large language models aren't going to be finding vulns anytime soon, which is a very understandable position. So with that backdrop, we're going to do a quick demo just to give you some context for what it actually looks like to work with the kind of data we're going to talk about, and then we're going to break it down. So here's the demo. You won't be able to see all of this, of course, but I'll describe it. Right now, I'm looking at a patch diff for a patch for a sensitive information disclosure vuln, and it's pretty busy. There are like 290 different functions. We're diving into the specific function that fixes a path traversal right here, and then we're going to take all of those functions and break them up into chunks, send them over to GPT-4, ask it to analyze and rank them, and figure out, given the patch and given an advisory, which of the changed functions most likely fixed the vulnerability. And we're running this a couple times, and the first time, it picks the right function and puts it right up top where I've highlighted, which is pretty encouraging. We then run it again, and we're going to scroll back up and look through the sorted list of like 300 functions, and it's near the top, but a little bit lower. There's some variability here that's important. We're going to get into that. But all said, our function that fixes the vulnerability ends up in the top 10% of the list of prioritized functions, which for a first go is pretty good. So let's go ahead and dive in into what others have done in the offensive security scene in terms of using LLMs for research. And just to place our attention in this problem space, we are specifically going to be looking at how to use large language models for static analysis of pseudocode that we get from decompiling a patch diff that is a diff between new code and old code. So we're not going to be doing fuzzing or dynamic analysis. We're not doing exploit dev or pen testing. There are plenty of papers that people are actively writing right now where they address those problems, that we're going to really scope in our focus on the static analysis problem. And if you were to look on arXiv, that's a popular site for finding any research papers relevant to some topic you're interested in, and you're looking for using LLMs for vuln discovery, you'll find these. There are a couple others, but I found these to be the most relevant. And I also plotted them according to date, along with major releases of various open and closed source large language models. And you can kind of see a trend. First of all, there's been a big cluster of papers released just in the past 6 months. It's kind of interesting. You also see a lot of these model releases kind of clustered together. A lot of the research didn't really come about until GPT-4 was published, which in some, that's not super surprising, right? Because it was kind of like a vastly more capable model than what had been available at the time. And I included the IDs of these papers, so you can look them up and read them if you want to, but I'm going to spoil it for you right now and summarize some of the key insights. First of all, GPT-4 just rules them all. You'll see several papers that where they were trying to do like one-day or n-day analysis, and they'll say, yeah, GPT-4 was like the only one that could hack even a single vulnerability. Or they'll say GPT-4 outperformed the others, even specific domain models. So GPT-4 is a generic domain model. It's been trained on a lot of data, but not for any specific purpose. It's just for general summarization versus a specific domain model like Llama Code, or Code Llama rather. And they find that they prefer general domain models for their ability to do longer, more coherent descriptions. Also, if you hit Caleb Sima's talk right before this one, you would have heard that context is important, and I would agree. There was one paper where they ran an experiment and they said, hey, GPT-4, here's some code, and here's a description of the vulnerability we're looking for. Can you find the vulnerability? And in nearly 90% of the cases, it was able to do that. But when it took away the CVE description, and it said, can you just find any vulnerability in this code? It goes down to less than 10%, which is pretty striking. And that would confirm that context matters a lot. Regarding human in the loop versus a fully automated approach, I already kind of touched on this, but we also shouldn't be surprised that human-in-the-loop tends to perform better, but it might not be for the reason you would expect. Something that really stood out to me was that a human-in-the-loop helps especially reduce the common failure cases. And the way I read that was it can help a large language model get unstuck on what might be an obvious problem to a human, but less so to an LLM. We also find that the size of the context window is difficult in that it just limits how much context you can send to an LLM, so we're going to have to find a way to deal with that. And then I already kind of spoke to the randomness we saw in the demo. In one instance, it took our fixed function and it put it right at the top of stuff we should look at, but then it put it lower. And that's due to a large language model's inherent non-determinism. You can give it the same prompt, same context, and it can give you a slightly or even greatly different result each time. And I included this graphic here just to show, it's kind of funny. One researcher said, yeah, we tried GPT-4 and it worked almost 90% of the time, and every other model was 0. So here are some of the takeaways that we're going to bring into our approach. GPT-4 rules them all, so we're not going to test that basic assumption. Rather, we're going to stick to a tried and true general domain kind of off-the-shelf model where there's very low barrier to entry. So that if we're making an argument that maybe you ought to use an LLM to help with patch analysis, then this one is super accessible. We'll also focus specifically on vulnerability identification. And what I mean there is we're not going to present some code and ask open-endedly, hey, are there any vulnerabilities here? We're going to specifically focus on giving some code and an advisory that describes the vulnerability we're talking about. Can you find where it is? Because it's going to be in there somewhere. We're going to focus on human-in-the-loop as well. And we're going to have to solve for the problem of small context windows and non-determinism. So with that overview of LLMs in the literature, I'm going to pass it off to Josh to give us a primer of end-day vulnerability analysis, and then he's going to dive into his own approach he took at taking a stab at this problem.
Yeah, test. How cool. Thank you, Caleb, very much for that intro. So we're going to start here at end-day, just a summary at a high level what end-day analysis is. For a just very broad overview, a 0-day is along the lines of not disclosed and not patched. A 1-day is disclosed but not patched, and an end day is disclosed and patched. So us having the patch is a really important part for the patch-diffing part of this talk. An end day lifecycle for us at Bishop Fox is we're looking at what we call emerging threats, but new vulnerabilities that are released, and there's a news cycle around it, usually hype. The security advisory is the starting place, and then we move to downloading and extracting the software. A lot of the things that we're going to be talking about here are network devices, so it's also like file systems that run on a router or gateway or things like that. Then we take the binaries that are important to the functionality addressed in the advisory. Usually it's the same ones over and over again, and we throw them into a binary diff. Then from the binary diff, we take someone who will manually analyze it, try to run it, try to see if we can recreate the crash, then if we can take the crash and turn it into an exploit, and then we can share it with everyone. Where LLMs really come in for us is that we don't think that it can replace a human doing manual analysis, but it could help us do analysis faster if we choose to analyze the most relevant to the advisory functions first. So then I don't have to waste my time on a bunch of cruft. I just get to go to the good stuff. So an example security bulletin that we're going to be talking through in detail is a Citrix advisory that went out last year around this time on their gateway device, ADC gateway. The description for 2 of them are like lower level bugs, or sorry, like lower score bugs, and then 1 is just unauthenticated remote code execution. So a lot to go on with unauthenticated remote code execution. But when we actually download, extract the software, and throw it into bindiff, this is kind of what we're looking at if you just sort by the things that have changed the most. Now, if anyone could tell me what the vulnerable function is based on that alone, that would be awesome. But I don't expect that because it took hours of looking, and that's okay. But in our haystack that you're looking at, this is the needle, this is the actual vulnerable function, this is what they added, a little check. I'm not sure if everyone can see it, but this little check is just saying, hey, actually, if this condition is true, this is an error case, let's jump out of here, which is really important for fixing their vulnerability, because if they don't jump out of there, there's a buffer called in the function immediately following that you can just start writing extra bytes in, and since there's no ASLR, there's no stack cookies, we just started doing dynamic analysis on where we send the request, specific endpoints with just like a ton of A's, and then we get our crash, we write our blog post, and since we've also made vulnerability checks and exploits around this. But instead of going into detail about this, I'll leave it for extra reading and homework if anyone's interested. So the real question is, can an LLM actually help us with doing this faster? And where we start from, the only way it's going to be useful to me is if we start from literally the advisory and our patch diff, and it is able to prioritize functions, if it's able to save me time. So the context that we have to give it is unauthenticated remote code execution, the 22 changed functions in bindiff, and we know what the end vulnerable function is, because, and we know the reason it jumps to a not supported feature. But how do we even begin to use an LLM for this? Like, the thing I showed you was a graph application. That's not text, really, per se. And all my LLMs are just doing text stuff. Can LLMs read code? Can they look at a security advisory? It's hard enough when, like, we're security practitioners and we look at advisory, and to get something meaningful out of it, we have to work kind of hard. So how does an LLM actually gain any real insight into it? And then how do we actually gauge that it's meaningful? And I just kind of touched on that. If it can save me any time, I'm starting off with that being meaningful. So to just zoom in on the end-day process that we're looking at, it's just this part for this talk, downloading, extracting, diffing, LLM stuff. So Python's great at downloading. Ghidriff is the tool with the cool dragon logo that can generate a patch diff that has a like text unified view. Great shout out to Clear Blue Jar, the developer of that. And then we'll take the text diffs that are coming out of it and feed it into an LLM. So even as a starting point, we wanted to know how well we could scale this. Everything okay? Oh, you're good, you're good. I was like, that just sounded like death. I was like, oh my God. So even if you're starting off with the question, can we scale this up? I want to know, do I have to ask, does an LLM need the context of, hey, you're a security researcher and here's the prompt, and then, or here's the advisory. A user prompt is me giving you a function and a diff, and then it giving me an answer, and then do I have to stay in the same conversation and feed it more function diffs so that it has the context of the previous ones to be relevant? Or can I split it up and just have like a parallel, I'm going to run a bunch of conversations simultaneously, get the results out. And when we're looking actually at an advisory, we're asking from a system prompt level, look at this advisory, look at this function, does it seem related? And overwhelmingly, they're like basically similar scores. Every once in a while, I think this is the biggest one at 25 difference. So like, I asked it to scale 0 to 100, do you think this is related to the advisory? And so since it doesn't do much better having multiple contexts, we were able to split it up and run everything faster, which made my life easier. So the next step is to analyze all the functions and see what it finds. Everything's a vulnerability. It's just telling me what I want to hear. All of these functions have to be related to the advisory. All of these functions are critical. And I just want to flame the LLM for a minute because we should never just blindly trust things. This is an example of a diff where the only things that are changing are the function names. It has underscore boundary check. That's great. So the LLM thinks that everything about this is terrifying. Base 64 decoding data is actually a legit attack vector. So I can see why it thinks that matters, but it doesn't. And so just rating it 95 out of 100 on some variable name changes is rough. So at first I thought I was to blame. I was like, can an LLM write a better prompt than what I can? Maybe I'm just messing up in my usage of it. Maybe GPT can write better prompts than me. So I took a bunch of security advisory, CWE descriptions. MITRE has guidance on how you can mitigate any CWE. And so threw that all into an LLM, and it generated a evaluation criteria for me. And I just went okay, look at the diff, look at this criteria, give me a score. And this is just kind of a example summarized of the criteria it generated. Sanitizing inputs is good, checking for authentication checks in an unauthenticated remote code situation is great. Error handling and logging, cool. Documentation's kind of lame, but maybe someone has written in a code comment, I guess is what it's going for. But this is, that was a summarized view. This is the real view. Please, no one have to read that. And then, so how does it do? It, again, puts this boundary check, again, as the best function that it can find, even with a better evaluation criteria. So we go back to the drawing board, and we say, okay, if we just give it a ton of context, this is not helping. We can't just do it all in one shot. Let's start splitting up the prompts. So the first thing to read this, oh sweet, you can see the mouse. So to read this, it is the security advisory in the function diff. We look to see if it's in the affected component, and we weed it out if it's not in the affected component at all. Since we knew that this was a function related to unauthenticated requests, I was trying to get it to take anything that's related to definitely an admin prompt or an administrative side of the diff and take it out. And then from if it's affected, look at the security advisory and the diff and give me a score. And then split it up even further into, hey, if it is affected, it's in the right component of the binary, and hey, now give me any security-related changes that you're seeing in this. And so that instead of giving it a full diff of kind of pseudo C code, we can work with a summarized view of what's happening and then give it a score. And that started working a little bit better because once it summarized what was security-related, it could then reason if the security-related information matched the advisory, so we're getting it closer to something that was in the same level of translation. So it was good at filtering out unrelated functions, but at best, it put our function at number 4, and so it could just be better. But we were figuring out that by having it reason in paragraph of hey, security-related changes, this is the advisory, it was similar language enough that it could start doing a better understanding of reasoning, really. And so if we just switch to, if something summarize the logic-related changes at the beginning, and then try to see if any of those changes in logic are related to security, and then if any of those security things are related to our advisory. We also added bin diffs results and ggdrifts together because they do find different functions as modified. I don't know if anyone else has run into this while they've been reverse engineering, but different diff tools will say different things have been modified. I think this for ggdrift is because it's looking at a decompiled view, And so if you decompile a bunch of stuff and variable names have changed, things that it will start saying that things have changed when things necessarily haven't, and that's just because it's working at like a pseudo C comparing diff rather than bin diffs like assembly level. So since we're working with different levels, we can get different benefits out of combining both and then weeding things out based on that cross-section. And the last final change that we make here is that every time that we get a score out, we feed it back into the LLM one more time to rank all the scores and all the functions against each other, because everything that we've been doing is in parallel and without context of the other functions. So by then combining it all for context and giving a ranked score against the other ones, we are finally getting closer. So our GW test handler comes up first, and we are actually able to find, like this is the thing that I actually didn't believe at first. Like it ranked my function as number 1, not 2, not 3, not 4, as it had never gotten this good. It never had gotten to adequately even describe that, oh yeah, coming close to the mic. The thing that I just want to highlight is that even its justification of being like, it is directly called by unauthenticated request, so it's a good candidate. It's handling unauthenticated, and then it also has more input validation improvements. And that's like the key of, as a person who's actually doing the analysis later, I want to find how it is changing my user input, like handling requirements, what checks it's adding, and we're actually able to find it. So, of course, now that we're able to get one vulnerability, find the vulnerable function for one vulnerability, we're extending to new ones. Can this actually work in the scale? Can we do it repeatably for other things? So 40OS had a bulletin for an out of bounds rate, in their SSL VPN. This has been quite a spring of different VPN bugs. So the function here is basically 40OS is different than Citrix that we've been working with before, because this is a binary that has no symbols. So the function names that we're using to reason what's the components, where in the binary is this, have all gone. We're just working with hex addresses. So that makes it's a new challenge, and this is just saying that it allows unauthenticated remote code execution or arbitrary code execution through HTTP requests. So it's not very specific either. But we ended up doing like the binary diff. We went through and started changing the prompts to say like, okay, you used to look at function names, don't do that, and updated the advisory. And in our first time just running with only changing the advisory information and not to look at symbols for our prompts, we got the actual real vulnerable function placed number 2. And that made me go, okay, but why number 2? And if I look at the function that it ranked number 1, there is actually a bounds check looking for like if this buffer overflow is happening, and I can tell just by the comment, common read request data, SSO body buffer too large, that it's dealing with like, oh, there's probably an overflow here. So maybe we found something else while doing this. But that was just an analysis I did over the weekend, so maybe I'll look more into that. Or you could. Also at the same time, in the same diff, there was a format string bug, and we happened to be seeing something reference format string bugs in our analysis of the other vulnerability that I just talked about, since it's the same patch. And so we were like, okay, well, what if I just ask it to look for format string bugs? If I just change the prompt to literally look for format string bugs instead. And that's what this slide is saying. And we are able to find it on the first slide, or on the first try, and we're able to see that A justification that it gives me for why it put this function first is there was a hard-coded, newly added hard-coded %s, which does mitigate normally like sprintf bugs. So new class of vulnerability, different diffs, different binaries, it's starting to work. And I was really surprised. And this is where I'll pass to Caleb.
All right, thanks, Josh. Let's pause and recap where we're at so far. Given an advisory and a patch diff, we can do a couple things. We can describe each of the functions that changed in the diff. So whereas you might just have some assembly or even pseudocode, we can generate a prose summary of what's happening in that change, which is pretty useful on its own. We can ask, is it a security-related change? We can estimate if that change seems related to the vulnerability that's described in the advisory that we care about, and then we can rank them according to the most likely candidates. Now, Josh and I were putting slides together for this talk last week, and another bug dropped in an SSL VPN appliance, and kind of looked at each other and wondered, I wonder how GPT-4 would have retroactively handled that patch. So let's take a look at this vulnerability in Checkpoint Quantum Gateway. This is probably a good time to thank Checkpoint for sponsoring this conference. Now, just to be clear, we're not going to disclose anything new here. There's been plenty of analysis already, like very quickly by some other third parties about this vulnerability, but we're going to look at it from an automated perspective. Could we have located the fixed function automatically? And just a quick overview on this, it's an arbitrary file read coming from the faulty use of the string. This is one of those you weren't really ever supposed to say out loud. There was a lot of code that changed in this patch, so this is actually a good test to see what happens when you have a much bigger denominator. Like, if you can find the right function, but there are only 10 or 20 or 30 functions, like, that's very helpful, but what happens when you get a lot more than that? So, did I say there were a lot of changed functions? There were a bunch modified, changed, added, deleted, and some of the techniques that Josh described start to break down at this scale. So if you had 10 functions that changed and you want to compare them all against each other, you can probably do that within the context window of a single call. But for this many, that doesn't work. And so we start to deal with some restrictions in the context window size, and we could address that in a couple ways. I mentioned before, yeah, we could try to just send all 300 functions into the same prompt, but that's not going to work. It's way too small. We could send each function separately to GPT-4 and say, like, score this one from 1 to 100, score this one, according to how likely it is to be related to the vulnerability, and then compare them all. But the problem with that is two things. First of all, LLMs just seem to have a tendency to inflate scores. If you caught Ben's talk yesterday, it's kind of reminiscent of CVSS. And it's also non-deterministic, as we mentioned before. So you might get a score that's not the same on this run as it is the next one. Now, when we ran into this, I mean, this was like over the weekend. We were looking at this and kind of like throwing our heads against it, feeling kind of stuck. We also heard Kimberly say in the keynote yesterday that if LLMs are unreliable 10% of the time, how can I trust them the other 90% of the time? And I think the answer is you don't. And instead, you use in this case, a sorting algorithm that helps mitigate the randomness and variability that you get from GPT-4. Said more simply, you just keep running it over and over and average the results. So this is a picture of the approach that we ended up taking. So we're just kind of like slamming code in on Sunday night, trying to get this working. And so you've got, in this very simple example, 15 different items. in reality, we're dealing with functions, but it doesn't really matter. And you want to sort these against one another. And the problem is your comparator, the thing that is comparing one thing to another, it's both like non-deterministic and it doesn't present an objective numeric score. So the idea is to give every item as much exposure to all the other items as possible. And it's hard to do that if you have a really small context window. So the way we do that is we break it, like in that first column. You take those 15 items, break them all into small groups of 3. You compare them against each other, and then record the scores. Then you add them all back together, shuffle them, take another sample, again, like groups of 3. You sort those, store the results. And then you do it again. And then you can average the scores across all the runs to get a sense of which are the items that just tend to be at the top most of the time. So for us, that's like which of the changed functions most of the time ends up seeming like the most likely function when compared to its peers in a random sample. And so this involves a lot more calls, but it doesn't get super expensive. I would estimate to do the run of the 300 functions that I mentioned before, I'd be surprised if it cost more than $10. It took like 3 minutes to run. It would probably be less than that. And again, 2 benefits. One is it just gives it as much exposure as possible. It also mitigates the risk that any single run will create an outlier that really skews your results. I call this multi-sample sort, but when I suggested to Josh we could call it average sample sort, he said that was not professional, and to finish your slides, because we're talking tomorrow morning. So here's what it actually looks like when we do that run. So again, we got like 293 functions. We know the function that we're looking for that fixes a path traversal. And in this case, we split those 300 functions up into groups of 10. So we have like roughly 30 groups of 10. And we randomly sample them and run this 10 different times. So 10 times that function is compared to a new group of 9 other peers. And there are 2 axes on this graph. One of them, the red line, is the score that our fixed function that we're looking for gets each time, like in every individual run. And you can see most of the time it gets like a 7 out of 10 or greater, or 8 or 9 or 10. So it tends to be ranked pretty high, but there are a couple outliers where it gets like a 1 and a 3. And it's like, what happened? I don't know. We'll get into that in a little bit, pretty shortly. And the other blue line is the running average of those scores for each run. So you can kind of see, in the beginning when we've just done 1 or 2 or 3 runs, the average gets like really thrown off by an outlier score, but it starts to stabilize over time when you get more samples and more exposure. And so we end up in the top 9%, which like for something we just did 2 days ago is like not bad. Presumably it could get a lot better with more investment and more research. As I mentioned before, there are a couple outliers that's notable, but again, the whole point of this technique, the point of running this over and over again, is to mitigate against those outliers really skewing the results. So it kind of compensates for the non-determinism that's inherent to an LLM. But let's look at those 2 outliers. Like when I saw those, I was thinking, what other functions was our fixed function being compared against, and how did it get ranked so low? Like what else could there have been? And so we've got the top 10% is like the top 30 functions that it ranked, and I bolded, you can check the slides later and read the words if you like, but the gist is the functions that it tended to rank highest did seem to deal with security-related issues, a lot of explicit brute force prevention, session handling, authentication, and then path traversal just kind of stands out. near the, again, this is like number 29 or so out of roughly 300. So still pretty high, but it gets a couple other functions in front of it. And when you consider the CWE that was accompanied with this advisory, that is exposure of sensitive information, like this, the advisory doesn't say path traversal, it says exposure of sensitive information. So it's suddenly not terribly surprising that it gets ranked high, but there's some other stuff that gets ranked above it. So we could keep tweaking our prompt, we could keep trying to add more context, but at the end of the day, whether for this vulnerability or for another, we may just have to be happy with a good enough job that puts it, say, in the top 10%. And that's something I could feel good about. I mean, personally, if the litmus test is, would you use this? Yeah, I would use this to prioritize my own manual testing. Now, just to kind of bring us to a close before some Q&A, this is the same recap I did a moment ago. You can describe the change function. Is it security related? Does it fix this given vulnerability? But we've also shown how we can use a multi-sample sorting algorithm to handle the limited size of the context window and also mitigate the non-determinism that we see in LLMs. And all of this, I don't think we're making any wild claims here, claiming that we can go from zero to hero and do fully automated vuln research. But if we're making the reasonable claim that a large language model can give a human researcher a much better starting place in their manual analysis with a lot more context, then that's an argument that I can make with a straight face. As far as further research, there are a lot of different ways that you could go if you wanted to improve this approach. I think giving more context, including full incoming and outgoing call trees, summarizing all the functions that call your own function, I think would be really useful too. We experimented with it a little bit, but in the limited time we had, we haven't explored it yet. Dynamic testing, using an agent to fuzz or try to crash the program given the vulnerability that it identifies. Using other models, not just using other vendors, which I think could be useful, but also checking out specific domain models, as we mentioned before. Some papers have found that general domain models work pretty well, but this landscape is changing all the time, and that would be worth taking a look at. Another interesting approach would be in the large language model's analysis of a diffs function, you could provide additional context, not just about the advisory, but also documentation about the product. Now, if you've ever browsed a vendor's docs for like an admin or a developer, there's a lot there, like way more than you could fit into a context window, but you could use RAG, retrieval augmented generation, to embed all of those docs, and then your model could look at a segment of code and be like, seems like it's related to this component described in the documentation, which is the same component mentioned in the advisory. So I think that'd be worth taking a look at. I'm not a statistician, but I was able to take a reasonable look at just averaging the different scores across the different runs, like I mentioned to you. There might be other summary statistics that might be more appropriate for mitigating against skew by outliers, so like a trimmed mean, or looking at a median instead. I'll call Ben out again, he's probably the right person to ask about that. And then, yeah, you could improve the prompts endlessly. So that brings us to the close of our talk. Again, it's up to you to decide if LLMs are truly gonna change the game or not, but I hope the evidence we've presented just gives you more to think about and consider that there's more than just a binary position on this issue. Thanks, and open to any questions. Hey.
So you mentioned a few times that LLMs were not very good at just saying how critical something was, and they always overstate
Yeah, I can name one thing off the top of my head. I'm sure Josh can too. I ended up throwing a lot of really angry words at the end of my prompt saying, do not under any circumstances overestimate the relationship of this vulnerability to the advisory. I also said, hey, just like be very conservative and skeptical in your analysis. So there are certain things that I tried to do to kind of dial it back down. But when it's just looking at one function at a time, and it's asked, like, how much do you think this one relates to it? I could not get it to stop inflating toward the upper end of whatever scale I would give it. Yeah, anything to add to that?
I think that was a great answer.
Yeah, that's a great question. Hey.
So, in this section where you were trying to improve it, you mentioned that you were having it summarize what the individual functions were doing and, correlating that to the security advisory.
Yeah.
And I'm kind of wondering where that sort of breaks down, looking at the individual function versus the context in which that function is used. And maybe it's that I'm not as familiar with the output of these sort of bin-diffing tools, but I would imagine that you would have to look at the full trace to that specific function and be like, I think you mentioned as well that it was like called from an unauthenticated request function. So how did you get access to that context?
Yeah, you want to take it?
Yeah. Part of it is the tooling that we used, Ghidra. Ghidriff is a Python API using tool plugging into Ghidra. And so when it runs and it generates its diff, it will give you additional function context, especially directly the function that called it and the functions it calls. Yeah. Also, big shout out to Ghidriff because it gives you strings that are added too in the diff, and that's been great for error messages. But anyways, does that answer your question?
Yeah, that's awesome.
Cool.
So yeah, you're right. Adding more context, like how does it get there, matters a lot. And so that was part of like you mentioned, there are some tools that'll give you just the names and the call tree, but I think also grabbing the content of that function, summarizing those two, putting the whole chain together, summarizing the whole flow of that whole path that gets you to that function would be pretty outstanding because that's what we do in our analysis all the time. Cool. Any other questions?
We got one other question.
Hey.
Seemingly more common question, but you're in a position of leadership or management.
Yep.
And you're advocating for sane usage of LLMs rather than fictionalizing everything.
Yeah.
I just want to say thank you.
Yeah, cool. So if you didn't hear that, it was an affirmation of augmentation versus replacement of humans, and yeah, could unpack that a lot. Is it possible or even right? But yeah, I agree. A balanced approach seems like the way to go. I think we have time for one more. Yeah.
30 seconds, cool.
The last thing I wanted to ask was, I guess, what was the way that you implemented GPT-4 to go against this? And was there any settings that you could adjust for temperature, which may help with the non-humanization of it?
Yeah, we used GPT-4 through Azure Cloud. We were able to play with things like temperature. So ours was at like a 0.2 where the default's like 1, I believe. And so we had tried to set it to less randomness. And now I'm officially getting the sign. But talk to me after. I'm happy to talk more.
Thanks, y'all.